based on electromagnetism. It is open loop, non-linear, and unstable, which makes them a great example of a controlled system. Such applications of these systems are fast maglev trains, space shuttles, and magnetic bearings. To control the system, it needs three basic elements. First, the plant, which is the dynamics of the steel ball. Second, the sensor, which is the photoresistor and the light emitting diode. And third, the proportional derivative circuit controller. The goal of this system is to levitate the steel ball at the desired height by making these two forces, the attractive force and the weight, equal. The amount of light received by the photoresistor will act as a signal towards the controller, and the controller adjusts the strength of the attractive force generated by the electromagnet.
Our system can be modeled in two mathematical equations, the mechanical and electrical equations. This is our mechanical equation corresponding to the forces acting on the steel ball. On the other hand, this is our electrical equation corresponding to the summation of voltages across the electromagnet. Unlike our electrical equation, the mechanical equation is non-linear because of this term. So we need to linearize it using Taylor series expansion for two variables by letting our variable I equals to delta I plus the initial current and our variable y equals to delta y plus the initial displacement. And now this is our resulting Taylor series linearized equation for our mechanical equation. To solve for our k, recall that at equilibrium condition, our delta y and delta I are 0 and the speed of our steel ball is also 0, which means that the second derivative of our displacement is also 0. Now, this is the value of our constant k. And then, we're going to solve the final linearized equation for the nonlinear term. And now, this is our linearized mechanical equation. Using these two linear differential equations, we can solve the system transfer function using state space equation. We let our state variables x sub 1 as our displacement, x sub 2 as the velocity of the steel ball, and x sub 3 as the current passing through the electromagnet. So, let us derive our state space equation. And now, this is our resulting state space equation, in which this one is our state vector, our input matrix, our state variables, and our output vector matrix. And by using matrix algebra, we can solve the system transfer function. And finally, this is our transfer function for our system, in which our output is the displacement corresponding to our input, which is the voltage.
Our system, we need 3/4-inch plywood for each housing using this dimension. And also, we need 1/2 inch by 3 inches PVC pipe and a white lead with 100 ohm hold-on resistor and a photoresistor for the sensor module. And for the controller and the electromagnet module, you need these following components.
The height of this PVC pipe should be adjustable to help during tuning, and the both pipes should be aligned with each other. Make 1000 turns for your coil.
This one here is our controller. It comprises two potentiometers for adjustment, two op-amps, resistors, a transistor connected to the heatsink, and this one here is our electromagnet perpendicular to the axis of the two PVC pipes, which are the LED and the LDR.
And now we are ready to test our system model. Plug in the power supply. This power supply is for the electromagnet alone, and this one from the computer motherboard is for the controller and the LED. But before turning the power supply on, make sure to turn on the knob of the potentiometers to its least resistance value, and then adjust slowly the voltage and current of the electromagnet as well as the resistance of these two potentiometers. Adjust this potentiometer, which is connected to the base of the transistor, to vary the strength of the attractive force. And then on the other hand, this potentiometer is connected parallel to the capacitor in order to stabilize the motion of the steel ball.